the part 10 of a series of videos dedicated to electronic simulation with thermistors and RTDs. In part 9, I showed how to complete an old analog thermostat simulation by adding a thermal circuitry and an NTC thermistor. Simulated this way, it is as relevant today as it was in the 1990s when it first appeared in The Art of Electronics by Horowitz and Hill. Today I would like to go further by showing that the Vishay Thermistors models with thermal modeling can be applied to any temperature control circuit imaginable. So, let's go for a few thermostats more.
We will begin with a very basic PI temperature controller. The ubiquitous Wheatstone bridge contains a sensor with a tunable response time and the same but virtual thermistor with the set temperature as input. The heat generated by the warming element and the NPN transistor are modeled as pure heat current sources, which are injected in the load or oven or any system to heat. Before we explain how these models were built in LTspice, let's do a transient simulation. The system temperature starts at 25 degrees C and increases linearly to end up at the defined set temperature, whether it's 40, 60, 80 or 100 degrees C. Then after that, the power is redefined in order to keep this temperature, even if the external temperature is changing. The upper pane represents the sum of the current of the sources V4 and V5, the two heat fluxes generated by the heating element and the transistor. Let's take the case of the transistor. We integrate the original transistor in the schematics and we make the proper connections. Now both transistors dissipate the same power. We point out the Q1 device and the Alt key with the small red thermometer displays the dissipated power in the virtual oscilloscope. The upper pane shows this power while the lower pane shows what current comes out of the thermal pin. We see that these curves are strictly identical. The dissipated powers are now fully effective parts of the schematics. The second circuit is another type of thermostat, this time an on-off control circuit with hysteresis. Under the threshold, the heating works 100%. And above this threshold, a fan cooler is switched on, which is here modeled by tuning the amplitude of this resistor, the thermal resistance, expressed in degree per watt, which is lower when the fan is on. There is another heat source, V power, which is communicated to the system under a time-dependent source. We are going to see how the system temperature is evolving following all these variations of external conditions. In the first simulation, the cooling fan is on above 30 degrees C. The system is submitted simultaneously to the influence of the external temperature, the application of the parasitic power V power, and above 30 degrees C, a better dissipation of the heat with the fan action. We see that the system temperature remains most of the time under 30 degrees C unless the external temperature is at the highest point and at the same time V power is on. In a second simulation, we remove the fan cooler and the system recovers its natural thermal resistance. This induces an overpassing of 1.6 degrees C above the set temperature. This new circuit is still an on-off temperature control where we have introduced an high-speed optocoupler, the 6N136, with a photodiode and a transistor output. A Silicon-X NMOS is also modeled with the heat power output. The thermal portion of the circuit is identical to the preceding presented thermostats. We can now study how the temperature control would be performed for different hysteresis resistance value and variation of the ambient temperature. So let's make two simulations with two different values for the feedback resistance. We see the overshoot above 60 degrees C. We see also how the power pulse frequency is driven by the ambient temperature changes. We are also able to define exactly the overshoot amplitude and the hysteresis in temperature in function of the value of the feedback resistor. In this last thermostat circuit, we introduce a new Vishay optocoupler, an optotriac VOT8125 this time, and also some logic circuitry easily rebuilt with the elements of the digital section of the LTspice libraries. The simulation results come as no surprise. The temperature control works effectively as foreseen. All the simulation presented in this video and much more can be downloaded on axter.io. Don't hesitate to go there and to download any simulation with Vishay temperature sensors. So this ends up the last part of our videos dedicated to electronic simulation with thermistors and RTDs. I hope that you enjoyed it. Thanks for watching.